Okay, good morning. Thank you for inviting me to speak to you briefly about a subject that I've been very interested in over a few years. So I've just joined Rise 6 North. I came from the University of Leeds. I'm actually on a long-term study leave from the University of Leeds, where I built up a research group looking at thermal and energy management of electronic systems. So it's all about the heat problem. We put energy into these systems and it comes out as heat. So this is a bit of a play on an interesting title, growing data, and the fact that these transistors are actually consuming small amounts of energy, but there are so many of them. So when do we reach the physical limit? So I thought I'd start with a provocative slide, and this is quite an old slide, and I used this a couple of years ago. So just to demonstrate the issue, things have changed. This was 2012, but you may remember this video. You may be one of the 2 billion odd people who actually bothered to look at this. But the importance of this is that it's actually the digital demand and the energy that we're talking about. So Time magazine at the time was reporting how much energy it costs to stream 1 minute of YouTube video, and it's a small fraction there of a kilowatt hour, 0.0002 kilowatt hours. And if you actually then look at how much energy you need to transform that, to transmit that data over our networks, there was a TED talk based a couple of years before this, and he was talking about the energy consumed in transmitting the data. That was about 0.01 kilowatt hour for a megabyte. And then there's the consumption at the end, the devices that we use to view the video. And I've assumed here about 0.001 kilowatt hour for 1 minute of video streaming. And then you see that this is a 17 megabyte file. It streams for 4 minutes. And in 1 year, there were 6 billion views of this video. And then you do the calculation, and you find that this uses 289, just this one video, gigawatt hours. Okay, it's a South Korean video that went viral, but the sad thing about it is that the energy that it's consumed is equivalent to a very poor country in Africa, Burundi. The electricity energy that they consumed in 2008 was 273 gigawatt hours. So it's a statement, really, on what we're doing. Okay, this is social media. And it's interesting we get into debates about the worth of data, the worthiness of data. So what I'm going to do here at this short time is just try and give you an idea of maybe how much energy we may be consuming in the future. And the problem with it is that okay, we have Moore's law, which we seem to be adhering to, but there's something else that's coming off of the curve that people are not talking about. This is an interesting paper that I read recently. It's about how much data do we need to store, how much data do we need to communicate, and how many computing instructions per second do we need to turn the globe in 2030. Okay, it's based on a number of statistics. It goes into a lot of detail trying to see how much data we're going to consume. But one of the interesting things I want you to look at is actually, I hope you know your prefixes, but this is zeta instructions per second for the amount of general purpose computing or special purpose computing. He divides it in the paper, they divide it into two different categories. And what I want to try and do is look at those instructions per second and the fact that the CPUs, the components that we use, consume small amounts of energy when they switch. And try and do a little calculation to show you how much energy we may be using in the future. That's the idea of the talk. There are physical limits to this, and the important thing is that we are governed by physics. The laws of physics we still need to adhere to. And interestingly, there was an article in Scientific American in 1971 relating energy and information. And the article was based on some work done by an IBM researcher, some of you may have heard of him, called Rolf Launder. And what he did is, in 61, he was looking at the limits of computation. He got very annoyed with a lot of people when we always assume that this data is ethereal. And we make it even worse today by saying it's in the cloud, that we can't touch it, but it's actually energy at the end of the day. It's actually consuming physical resource. And of course, Feynman, in his lectures on computation, talks a lot about this relationship between information and energy. And that gives us a physical limit, actually, some of these ideas. So, let's see. So if you do some calculations on the processes over the years, and I managed to, based on the heat fluxes and the number of transistors that are switched on, of course, you can see that the switch in these transistors is consuming a certain amount of energy. Now, a zeptojoule is 10 to the minus 21 joules. It's a very small amount of energy. And what you can see here, the latest processors here, this is the feature size. We're getting down to around about 10,000 zeptojoules for the switching in one transistor. So if I wanted to work out the power that particular transistor is consuming, I would multiply it by the frequency at which it's switching, and that would give it the power. So, but what's happening since probably 2008, because of the Dennard scaling issue, because we've gone multi-core, is that not all your transistors are aligned at once. Because if they were, we would be over the power budget of the CPU. So there's this era of dark silicon, and it's difficult to get a lot of information on this. There are papers on it, and nobody really knows how much of the CPU is actually operational at any one time. So what's the future there? Well, the interesting thing about this lower technology here is it's nominally called 2.5 dimensional. So, the technology going forward is starting to look at 3 dimensions. This is the FinFET technology, those of you might know anything about that. So, okay, we're at maybe 10,000 zeptojoules. What is the actual physical limit? So, if you go back to that paper where in 2007 it was talking about the amount of energy consumed, the amount of instructions per second that we need to turn the globe in 2007, what I did is I then did a quick calculation based on the fact that if you take an instruction per second, an instruction to be involving 4 transistors, because usually a logic gate involves 4 transistors, and then you scale it up with the amount of instructions per second you need, you actually get an interesting curve here. This is, whoops, that's the wrong button. This here is the percentage of global energy consumption, depending on the speed at which you switch. So by about, if we're switching at 2 gigahertz, we're consuming 1% of our electricity in 2007. And there was a paper here which was looking at the consumption of ICT between 2007, energy consumption of ICT between 2007 and 2012. And interestingly, the servers in the data centers here were using around about 100 terawatt hours per year in 2007. And that equates to about 0.5% of our so those curves sort of agree by that calculation. So I thought maybe I can now use that to predict going forward. But this is an interesting graph here, because for a long time, this is the energy consumed by the switch. And for a long time, from the early days of the 40s here, the energy consumption was on a log linear straight line. Until early 2000, we sort of stemmed off this now. And these are some of the predictions here from the International Technology Roadmap for Semiconductors. The switching, 10 to the minus 18 is an attojoule or 1,000 zeptojoules. So we're looking by 2030 that we can get to about 1,000 zeptojoules for the switching in a transistor by about 2030. But what's also interesting is that Landau did actually, based on Boltzmann's H theorem, or actually if you link it to Shannon's information theory, you can actually get this physical limit. So he was saying that the actual limit you can possibly do is 3 zeptojoules. That's the maximum we can get to. And then there's a whole raft of papers that disprove that. Oh gosh, is it really 1 minute left? Right. But didn't I start 5 minutes late? You're putting me off. But if you look at Bennett did some work on how biologically the DNA polymerization process, every step in the DNA polymerization process costs 174 Zeptojoules. So if we used biochips, or we used biologic nature, as it were, as a switch, then we could only get down to about 175 Zeptojoules for the energy consumed in an instruction. Yeah. And then Frank did some work on the possibility of lowering the voltage, because that's one of the issues. We need to lower the voltage in the because you're dropping a voltage to ground, and that's where you dissipate energy. If you could lower the voltage, but then there are some probabilistic issues that your processing becomes a little bit statistical, and that's not really ideal with a deterministic machine. So he reckons 435 Zeptojoules. So, well, okay, now we have a range of different, so we have the ITRS saying 1 attojoule, which is 1,000 Zeptojoules. We've got biology, we've got the guy Frank, and we've got Lowndes. So it's 4 different limits. So what about if I then took what that paper was saying in 2030 and try and predict how much energy we'll be consuming in the future? And what you can see here is the different curves here. This is the green curve is the ITRS, the blue curve here is Lambda. That's the ideal. So yeah, even if we were switching at 8 gigahertz, we would only be consuming 1% of our electrical consumption based on 20. I've still got 1 minute left. Okay. So there is an issue here. Obviously digitalization is causing a huge growth, and it's not happening just in developing world. Developed world is happening in the developing world as well. I've just recently come back from China, and they are use smartphones for almost everything, and everybody has one. So demand will outstrip physical limits potentially, unless we can come up with a different switching technology. But there are things that are happening, and one of the interesting things is that there was a Future of Computing conference based on rebooting computing in November 2017, and two of the guys actually said, the last 30 years have been boring. It's now interesting. So we're getting into an interesting time because we've got to use new materials, we're going to do new ways of trying to process this digital information. But what this particular graph shows here from ISSCC proceedings is that if we go more heterogeneous, if we use more application specific and we don't use general purpose stuff, we will end up being more efficient. So maybe that's the way to go. And I am really getting hustled here from having 0 minutes left. But I've just got 2 slides left, if I may. One of the things is that this is the heat that's generated. So when we moved over to CMOS technology, the heat disappeared. So in the early 90s, CMOS technology, we started to see the heat fluxes go up. Look at these now, we're getting heat fluxes of, that's almost a megawatt per square meter. And if you look at nuclear reactors, they're about a megawatt per square meter. So these are small, if you add them all together in a data center, you've got a large amount of energy there to deal with. So how do we deal with it? Well, one of my interests is actually not using air, it's actually using liquids, because this is a much better way of extracting the heat. And I don't have time to tell you here, but I've worked with a range of these fluids on a number of experiments, which I can't show you here today, but I'm here all day if you wanted to ask me about it. But some of them are fluorochemicals in vapor formation, some are water, and some is actually oil, using transformer oil, or mineral oil. So with that, I will finish, because I know we're running out of time. So thank you very much.